Clara, can you share your screen?
Yes, can you guys hear me?
And we can hear you.
Awesome. And can you see my slides?
Not yet.
Not yet. Oh, here we go. How about now?
Looks good.
Sweet, thanks. Hi, everyone. Before I start, I'd like to apologize. I meant to be there in person. Last week, I ended up getting pretty sick, and about the time that I got sick, a bunch of my coworkers tested positive for COVID, so I just wasn't sure how travel was going to work this week. Feeling mostly better now, but still a little bit out of breath, so please bear with me. But thank you for accommodating the last minute virtual talk. All right, so this is really going to be an introductory talk. I don't expect most of you to have necessarily heard about the soil moisture remote sensing technique that I'll be talking about today. So first, I'd like to introduce myself. Then I'll give an introduction to something near and dear to my heart, which is GNSS reflectometry, or GNSSR. And then I'll also take a little bit of time to introduce the company where I'm currently working, Muon Space, and what we're doing in terms of soil moisture remote sensing. And I only have two goals today. I want to convince you that GNSSR is a cool technique to retrieve soil moisture from satellites. And then secondly, I hope that some of what I talk about today will be interesting enough to some of you such that you might want to collaborate with us in the future. But first, just a little bit about my background. So I started a PhD program at the University of Colorado back in 2010. And on my very first day of grad school, I traveled with my advisor to Oklahoma to learn about soil moisture sampling and how to install soil moisture probes. And that's a picture of me looking at my advisor who's sitting in a box. And on that very first day of grad school, I met Mike Kosh and Tyson, who were both really helpful during my PhD. And my PhD project was to repurpose geodetic quality GPS stations to be soil moisture sensors. And I'm showing one of the GPS stations down in the bottom left. So there are hundreds of these stations throughout the US. And it turns out that some of the data that they record is sensitive to fluctuations in near surface soil moisture. Okay, so the data that they record is the part of the GPS signal that travels from the satellites, it bounces off the ground and then hits the antenna. And this is called the surface reflected signal. And if you look at how the surface reflected GPS signal changes over time, you can infer how soil moisture changes. And so my dissertation was to figure out a retrieval algorithm for soil moisture using these surface reflected GPS signals. And the outcome of that dissertation was the creation of a new soil moisture network, which was called PBO-H2O. And in the bottom right of that photo cluster on the slide is just a depiction of where our sites were. But since my PhD ended, I've been on this 8-year journey from being a postdoc to being a soft money researcher to now working on a private company to answer this question, which is, can we also use ground reflected GPS signals to measure soil moisture from space? And that's what I'd like to talk about now. This technique that I've been describing is called GNSS reflectometry, or GNSSR. So if you launch a modified GPS receiver on board a low Earth orbiting satellite, and then you let it record these surface reflected GPS signals, then you actually find out that they're pretty sensitive to changes in the moisture content of the surface. And this is because they're at the L-band wavelength, which is the same wavelength used by other soil moisture satellites like SMOS or SMAP or the upcoming NISAR mission. So all of our data is L-band, so it's sensitive to soil moisture in just the top 5 centimeters of soil. Now, this technique is relatively inexpensive compared to other remote sensing instruments. NASA's SMAP satellite cost around $1 billion for one satellite, but the satellites that I'll be talking about today cost around $150 million for 8 of them. And because it's inexpensive, you can launch a whole bunch of these satellites, creating constellations. And constellations of satellites lower your temporal repeat. So with a fully built out GNSSR constellation, you could potentially get global data at a sub-daily cadence. And then, of course, talking about spatial resolution is important in remote sensing. Our spatial resolution actually varies depending on the roughness of the surface. So sometimes our resolution could be as small as 500 by 500 meters, or sometimes as large as 25 by 25 kilometers in the most rough, tough environments. But for today, let's say a lot of the Midwest or say Texas, we estimate that the resolution is closer to maybe 3 by 3 kilometers, so a couple kilometers, but it's still a topic of active research. And this isn't just an idea. There are already a few different GNSSR constellations in space or that are planned to be launched soon. So the first is NASA's Cygnus constellation, which stands for Cyclone GNSS. As I said before, it's a constellation of 8 satellites that's currently orbiting the tropics. And today I'll be focusing exclusively on data from Cygnus. And then you have data from Spire Global, which is a private company, and they currently have 4 GNSSR CubeSat satellites on orbit. And then finally, you have where I work, Muon Space, and we're going to launch our first GNSSR satellite early next year. So this video shows data from the Cygnus constellation over a period of 24 hours. So the satellites collect data in kind of a weird way. Those of you who work with satellite data are probably used to data being collected in swaths, but we collect data in these sparsely sampled and somewhat random tracks. However, over time, these tracks of data fill in and you can start to make spatially complete maps of the data. So here, anything you see in blue or pink could indicate either topographically flat areas or areas with high soil moisture or with a lot of surface water presence. And if you look at how the data change over time, then it's easier to understand its relationship with soil moisture. So this slide shows our empirical sensitivity to soil moisture, in this case over northern India and Pakistan. So these were some of the first results coming out from the Cygnus mission that showed that changes in our GNSSR signal, which I'm showing on the left, are really well correlated with changes in soil moisture, in this case from the SMAP satellite, which I'm showing on the right. And since these first indications of this sensitivity came out, there's been a whole lot of activity within the community to develop retrieval algorithms for the data. So this is one example of data from just one retrieval algorithm that I developed at the location of one of the US CRN sites in Texas. The in situ soil moisture data are in blue, and then we have comparison satellite data from SMAP, which are in green, and the soil moisture data that we developed from Cygnus are shown in pink. And all 3 time series follow each other pretty well, but because Cygnus has 8 satellites and a faster temporal repeat than a single satellite like SMAP, we're actually able to observe more precip events. And I'm showing 2 examples of that near the yellow stars down in the zoomed in image on the bottom. So during these days, there was no SMAP observation, but there was a Cygnus observation. So you're able to capture that soil moisture variability. And you can start to do all kinds of cool stuff with the data. And here I'm just showing one application where you can begin to quantify soil moisture memory. So we looked at Cygnus data and we found that on average, the land surface retains about 53% of water falling as precip after 1 day, whereas after 2 days, about 37% is left. And after 3 days, only 17% of the water is left in the soil. And this agrees pretty well with the 3-day estimates from the SMAP satellite. So I think these data are super cool, but there are 2 major problems with them. And the first is that in some areas, the current Cygnus soil moisture retrieval algorithm is really underperforming. So on the left, I'm showing a density scatter plot of the Cygnus soil moisture data versus SMAP data. And there's a large amount of scatter, particularly with Cygnus overestimating soil moisture in areas where soil moisture, at least according to SMAP, should be pretty dry. And then second, at least currently, NASA has no plan for a follow-on mission to Cygnus. So once Cygnus dies, that's it, right? But these are 2 problems that my current company, Muon, is going to hopefully help address. We've developed a better algorithm based on machine learning that more successfully retrieves soil moisture from Cygnus. And I'm showing that in the density scatter plot on the right. Muon also plans to launch a constellation of GNSSR satellites to provide continuous soil moisture data in the years to come. And that's what I'm going to talk about now. So this brings me to the last part of my talk, just to introduce Muon and give a really, really short intro to our retrieval algorithm. As I just said, we're planning on building out a complete constellation of these types of satellites, as well as constellations of other types of sensors, specifically for the purpose of measuring variables related to Earth system science and climate change. So these are things like soil moisture, inundation extent, and particularly variables related to wildfire. We launched our first satellite, which we call MUSAT-1, back in June, and it appears to be operating really, really well. And as I said before, we'll be launching our first GNSSR satellite in early 2024. And we currently have a contract with the Air Force Weather Office to provide soil moisture data from this satellite to them, along with ocean wind speed data. This is just a very, very brief overview of our retrieval algorithm approach. I'm not going to go into the details, but we're using deep learning models, particularly convolutional neural networks, to retrieve soil moisture using the GNSSR data. And since we don't have any of our own data to play with yet, we're practicing by developing our algorithms with Cygnus data. So we train our models with SMAP soil moisture data as a target, and then we validate our retrievals using data from the International Soil Moisture Network. So here's an example of what the data look like during our validation time period, where we no longer need SMAP data to inform the model. So these are maps of seasonally averaged soil moisture from the Muon algorithm on top, and then the SMAP soil moisture data on the bottom. And generally they show very similar spatial patterns. And then here's a snapshot of our validation statistics. Data from Muon are at the top and data from SMAP are at the bottom. Each one of these dots is the unbiased root mean square difference between our satellite soil moisture retrievals and then soil moisture probe data from the ISMN. So darker colors indicate lower UB-RMSD and vice versa. There's a histogram showing the distribution of errors on the right, and you can see that we are within family of that of SMAP with the distribution peaking around 0.04.
Clara, you have 2 minutes.
Thank you. And then here's the same thing, except now I've colored the dots by the correlation value. In this case, darker colors are higher correlation. And when we look at the histograms of the correlation, we do see that we are underperforming relative to SMAP overall. But this is still an area of active research, and we're trying to improve our CNNs along with better ancillary data sets more suited to our particular type of signal scattering. And then I'll just leave my final slide up here. Please email me if you'd like to work together or if you have any questions. I'm always looking for collaborators. And if you have any questions right now, I'd be happy to answer them.
Great, thank you, Clara. Do we have any questions?
Yeah.
Two questions. One, do you guys also use or consider GPS GLONASS Galileo signals? And two, do you use anything like Jupyter notebooks for your code, for the data retrieval, station selection, masking requirements, things of that nature?
Yeah, those are two great questions. So the Cygnus constellation can only receive signals from GPS, but we call them MUSATs. We're going to be receiving data from at least Galileo and then I think GLONASS in the future. And then with regards to your second question, yes, we're totally a Python shop. I had just coded in MATLAB for the past 12 years. And when I joined Muon, I had to learn Python, and it's still kind of a constant struggle for me, but many other people in the company are very good at Python and use Jupyter notebooks. Yeah, that's pretty much all we use. So